Okay, folks, the secret to the rest of our time today is you already know how flux is controlled through pathways. We just hadn't discussed it yet. So I'll remind us of how we draw pathways, either with activators pointing towards enzymes or inhibitors with a blunt-ended arrow pointing towards an enzyme. So the first big way that flux can be controlled through its rate determining steps is inhibition. Okay, we have learned about competitive inhibition. We have learned about non-competitive inhibition. We have learned about mixed inhibition. Additionally, we learned about allosteric inhibition. This type of inhibition can happen at the active site or at the allosteric site. And on this screen, I have an example of what looks like feedback inhibition happening. So flux through this pathway, for example, is being controlled at the rate determining step through, looks like, feedback inhibition. But in addition to inhibition, we can have covalent modification that alters flux. And we learned an example of this as well, right? Phosphorylation of the enzyme phosphorylase is a way to modify flux if we're controlling a rate determining step. We do, of course, have one new example of a way to control flux through rate determining steps, and this is called a substrate cycle. So on the right-hand side, we see a pathway where A is being converted to D. So flux through this pathway would be defined by how much A is converted to D over time. The rate determining step is F. We should understand that step F cannot be reversed because that rate determining step most likely is exergonic. It's got that large delta G, and we don't have enough energy to reverse it, so it's irreversible largely. However, in comes a substrate cycle. A substrate cycle is an opposing reaction or enzyme, or R. So R is the enzyme that forms the substrate cycle. Now R, as it appears, is also another rate determining step. However, it's pointing in the opposite direction. So now we have added an additional step, an additional enzyme. This is going to help us increase our control over flux from A to D because we have a new enzyme, and this new enzyme can also be allosterically controlled, inhibited, etc. And keep in mind, we need to have substrate cycles as a part of metabolic pathways because rate determining steps are not reversible. So how do we reverse the pathway? By bringing in a new enzyme that can reverse the reaction, but it reverses the reaction in a new way, right? It's performing a slightly different mechanism, for example. So this also helps us to control flux from A to D. Not only can we target F, but we could have R, which on its own reverses the pathway, but then can additionally be a new enzyme to target. Finally, this is outside the scope of this class, but you can modulate flux through a metabolic pathway by impacting transcription and translation, how much of the various enzymes are present. Should we make more of an enzyme or less of an enzyme, for example? But that is really a long time scale control. Think more like what you'd learn in a genetics course or a cell signaling course, or potentially even in biochem too. For this class today, we will not worry about it. And that is all, folks. We've learned that many metabolic reactions are at equilibrium. However, those rate determining steps are the important ones for controlling flux. And we'll focus on rate determining steps for sure for the rest of this course. We learned some ways that we can control flux, most of which we already knew, right? Targeting them for inhibition or activation, covalent modification through phosphorylation, for example, and by substrate cycles. And that ends our introduction to metabolism.